Let's jump straight into this explainer, guys. Today, we're uncovering the epic, literally world-altering cosmic forces that have completely rewritten our planet's water and carbon cycles over millions of years. We're talking about a grand scale here, where Earth completely transforms, flipping from lush green paradises into relentless frozen wastelands. For your A-level geography exams, getting a solid grip on these long-term changes to Earth's life support systems, or ELSS, is absolutely crucial. We're basically looking at the ultimate cause and effect chain of planetary climate. But before we trace the ultimate power scaling of Earth's climate, we really need to ask ourselves a crucial exam question just to lock into that systems-level mindset. Does a massive shift from a cold glacial period to a warm interglacial period represent a steady state, or is it a dynamic equilibrium? Keep that in the back of your mind as we explore exactly how our planet balances its stores and flows of water and carbon over frankly unimaginable timescales. Consider this your mission briefing. We're going to cover Earth's climate pendulum, cosmic triggers, amplifiers, water cycle impacts, and finally, carbon cycle impacts. Let's kick things off with Section 1, Earth's climate pendulum. So, looking back at the vast Quaternary period, which covers the last 2.6 million years, our planet has experienced these massive rhythmic shifts. The data etched deep into Antarctic ice from the Vostok ice core brilliantly illustrates this planetary heartbeat over the last 400,000 years. You can clearly track 4 major glacial cycles in the data, with each one lasting about 100,000 years. It's like a giant roller coaster. You trace the sharp, jagged peaks of those warm interglacial periods and then follow the slow, relentless plunge right back into deep, freezing glacial maximums. Now, for your exams, you absolutely want to anchor these vital stats in your memory. The difference between a glacial maximum and an interglacial period is just staggering. We're talking about an average temperature range of up to 13 degrees Celsius globally. During the coldest periods, temperatures plummeted 9 degrees below the average, and carbon dioxide levels in the atmosphere dropped to just 180 parts per million. Then, in the warmest interglacials, those temperatures soared to 4 degrees above average, with CO2 swinging way back up to 280 parts per million. That is a massive 100 parts per million swing in atmospheric carbon between those two extreme states. Moving into Section 2, Cosmic Triggers, specifically the Milankovitch cycles. So what's the actual inciting incident that unleashes these icy transformations? I mean, what cosmic trigger is powerful enough to plunge an entire planet into an ice age? Well, a brilliant mathematician named Milutin Milankovitch figured out that our planet's orbital mechanics completely dictate its energy budget. He identified these long-term natural cycles in the Earth's movement that can alter the amount of solar radiation reaching us by up to 30%. This, essentially, serves as the ultimate cosmic trigger for global cooling or warming. Let's break down the mechanics of this. If you're writing an exam answer, using the Peel structure, point, evidence, explain, link, is a really great strategy here. So let's make the point that orbital changes trigger glaciation. The evidence, that's found in 3 distinct planetary cycles: eccentricity, tilt, and precession. You then explain that these alter the Earth's position relative to the sun, which naturally changes our solar energy input. And finally, you link this variation in solar energy directly to the start of an ice age. Boom! Perfect structure. Now, notice the totally distinct time frames for each of these cycles. Eccentricity, which is the shape of Earth's orbit stretching from circular to elliptical, operates on a 100,000-year cycle. Axial tilt, the change in the angle of our planet's axis, runs on a 41,000-year cycle. And precession, which is kind of like the gradual wobble of a spinning top, works on a 22,000-year cycle. When these 3 independent cycles align perfectly to minimize summer sunshine in the northern hemisphere, well, they slash the incoming solar radiation and tip the planet right into a new glacial epoch. Which brings us to Section 3, Amplifiers and the Albedo feedback loops. Here's the thing, though. A slight orbital cooling isn't actually enough to freeze a continent on its own. The Milankovitch cycles are just the spark. We need a planetary power multiplier. The initial cosmic cooling sets off this relentless positive feedback loop, driven entirely by the growth of northern hemisphere ice sheets. Now, just as a quick reminder, a positive feedback loop in systems theory is basically a mechanism that amplifies a change, pushing the system further and further away from its original equilibrium. Here's exactly how that feedback loop plays out step by step. Step 1. The Milankovitch cooling allows winter snow to survive through those cooler summers, so ice sheets begin to grow. Step 2. As snow and ice aggressively expand, their brilliant white surfaces drastically increase the Earth's albedo. And remember, albedo is just the measure of how reflective a surface is. Step 3. Because of this super high albedo, way less solar heat is absorbed by the ground. Instead, it bounces right back into space. And finally, step 4. Because less heat is absorbed, the Earth cools even further, which creates even more ice. The whole cycle just cascades, eventually locking the planet into a deep freeze.
All right, let's look at the terrestrial impacts in Section 4, Rewriting the Water Cycle.
Let's see how these cosmic triggers physically conquer Earth's life support systems. So, 20,000 years ago, during the last glacial maximum, ice up to 1 kilometer thick completely submerged regions like Scotland, Wales, and northern England, literally buried under a kilometer of ice. Compared to the dynamic water cycle we know today, this massive physical barrier violently interrupted typical evaporation and precipitation pathways. The land was entirely swallowed up. Bringing back our peel structure for the exam, the water cycle slows appreciably during a glacial period. Why? Because massive amounts of water are forcibly evicted from the ocean reservoir and trapped on land as solid ice in the cryosphere. This net transfer causes a dramatic 100 to 130 meter drop in global sea levels. On top of that, those freezing temperatures result in far lower rates of evapotranspiration. That means the dynamic flows of water moving between the Earth and the atmosphere basically slow to a crawl. The entire cycle just becomes sluggish.
Moving on to Section 5, Glacial Impacts and the Carbon Cycle's Seesaw.
As the oceans empty out and ice sheets conquer up to a third of the continental landmass, the carbon cycle experiences an equally dramatic upheaval. We see this massive systemic seesaw effect taking place. As advancing ice sheets destroy extensive tracts of forest and grassland, the area covered by vegetation obviously shrinks. This drastically lowers net primary productivity, or NPP. So with fewer plants photosynthesizing, carbon storage shifts dramatically away from the living terrestrial biosphere. But as we know, that carbon has to go somewhere, right? To explain that missing atmospheric CO2 during an ice age, and remember, it drops all the way down to 180 parts per million, scientists point to two massive alternative carbon vaults. First, huge amounts of carbon become sequestered in expanding permafrost as tundra replaces those temperate forests. Second, the oceans step up to the plate. Altered ocean circulation brings nutrients to the surface, stimulating these massive phytoplankton blooms that trap carbon and carry it all the way down to the deep, freezing ocean waters when they die. Plus, colder water is simply able to dissolve more CO2 anyway. So the carbon shifts entirely out of the atmosphere and biosphere and goes right into the deep freeze of the oceans and permafrost. To quickly summarize the core concept of our explainer today, long-term climate oscillations, driven by those Milankovitch cycles and amplified by the albedo effect, completely restructure our planet's major storage reservoirs. They slow down the vital flows of both water and carbon. It is honestly a stunning display of planetary dynamic equilibrium in action. I'm going to leave you with this final provocative thought to chew on for your exams. As we've just seen, it took a perfect cosmic alignment of orbital mechanics and a 100,000-year process to naturally shift atmospheric CO2 levels by about 100 parts per million. Today, human activity has caused a very similar leap in CO2, but we've done it in just a little over a century. So what does that say about the unprecedented speed and sheer force of our modern climate alterations? Keep questioning, keep analyzing those systems, and I'll catch you in the next explainer.